Today's discussion centers around the nature of gases. Before we can begin to talk about gases, we need to know that gases are compressible, expand to fill their containers, and are essentially all going to behave the same under normal conditions. The first law that we'll discuss is Boyle's law, which is the pressure-volume relationship for a gas. It says that the pressure and volume will multiply to a constant as long as the temperature and quantity of moles are also constant. So, mathematically, this says that P1 times V1, the pressure and volume under a given set of conditions, will equal the new pressure and volume, P2 times V2, multiplied together, so long as the temperature and quantity are remaining constant. A sample problem says if 700 milliliters of gas at 2.5 atmosphere pressure is expanded to 2.8 liters, what pressure does the gas exert? We can rearrange the equation here for the new pressure, P2. Doing so says that P2 equals P1 V1 over V2. So we can see that the pressure is going to be related to a ratio of the volumes. 2.5 atmospheres times 0.7 liters, we're expanding to 2.8 liters, and so my new pressure is 0.63 atmospheres, much smaller than initially. This makes sense if you think about it. If I expand the volume into which a gas is constrained, the collisions of that gas with the container wall should be less, and so the pressure should drop to accommodate that. The next law we'll talk about is Charles' law, and it is the volume-temperature relationship for a gas, which says that the ratio of volume to temperature is constant as long as volume and quantity remain the same. And so what this is telling me is that since volume equals temperature times a constant, a ratio of volume to temperature should equal a ratio of a new volume to a new temperature, or V1 over T1 equals V2 over T2. A sample question for this looks something like what we see below. At what temperature would the volume of a balloon containing helium at 25 degrees Celsius reach half its original value? And so we're looking for a temperature when the volume will shrink by half. So we're looking for T2. So we will rearrange this to solve for T2. That says that T1 over V1 times V2 is going to give me the new temperature. Substitution will be allowed here. We've got 25 degrees Celsius. Something we should note, gas laws always depend on Kelvin. Kelvin is the absolute temperature and is directly related to molecular motion. So all gas laws being based off kinetic molecular theory, which is coming in a later lecture, must use Kelvin temperatures, never Celsius. And so we'll convert this by adding 273, and we see that 298 Kelvin divided by V1 is equal to V2, which we said is going to be half of the original volume, so 1/2 of V1. A little creative algebra tells me that the V's will cancel out, V1 will kill V1, and so I'm looking at half the temperature to get half the volume. And so I see that I've got 149 kelvins. This makes sense too based on kinetic molecular theory if we think about it. Molecules or atoms that are moving at high temperature are moving more frequently with more energy. So when they collide with the walls of a container, they're able to push it out if it's expandable. As we cool them down, they lose their ability to push. And if we're in a container that's elastic, like a balloon, for example, then if they're not pushing on the walls as hard, then the balloon will shrink down until it achieves stasis between atmospheric pressure and the pressure they are exerting on the walls. The next law we need to discuss is Avogadro's law. Avogadro's law relates the volume of a container to the amount of gas inside it, as long as temperature and pressure are constant. And it's very similar in form to Charles' law. It's a quotient. So the volume mole quotient is going to be a constant. So V1 over N1 will equal V2 over N2. So the more moles of gas I place into a container, it should make sense that we'll get more collisions and the container should swell if it's elastic like a balloon. Or if I remove moles of gas, it should shrink like a balloon does if it's elastic. And we know this because we've all done this. We've blown into a balloon and seen it grow, let air out of a balloon and seen it come down. A sample problem for this says what will be the new volume of 5.6 liter nitrogen balloon at STP, and if additional 0.5 moles of N2 is added. Now, something that we have to note here, it's not that we're multiplying by 0.5. It's not that we're just saying, hey, I've gone up to 1.5. We need to know how much was there originally so we can add the 1.5 to it. I have to know the total number of moles at the end. So essentially, this would be like we've got this balloon and we're going to blow some more into it, only we're blowing pure nitrogen. And so we're going to solve for V2. V2, the new volume tells me that V1 over N1 times N2 should produce this. And I know that the original volume is 5.6 liters. And I know that the new number of moles is 0.5 higher than the original. But that's all I know at this point. I don't know what that original number of moles is. And so we need to do a little mole conversion based on what we know about conditions at STP. At STP, every gas occupies 22.4 liters per mole. Since I was originally at STP and had 5.6 liters of nitrogen, I can track that to how many moles of nitrogen gas that is. So my 5.6 liters divided by 22.4 liters per mole tells me that I have a quarter of a mole to begin with, and I want to add an additional 0.5 moles to that. And so I'm going to bring the total mole value up to 3 times what it was originally. And when I do that and substitute in for N1, where I have 0.25 here and 0.25 here, I see that my volume goes up by a factor of 3. Again, because this part of the equation, the N1 plus 0.5, is now 0.75, which is 3 times my original. So I put 3 times the amount of gas, I get 3 times the collisions on the walls, and because the container is elastic, it swells to equal out the pressure and temperature that must remain constant. Last but not least of our gas laws, special case gas laws today is the Gay-Lussac law. The Gay-Lussac law relates pressure and temperature and says that the quotient of these two is constant as long as volume and quantity of gas are constant. So as long as I'm in a sealed container that's not elastic, we're not talking about a balloon now, we're talking something like a cylinder. This pressure temperature quotient will be the same as long as I don't change that volume or the amount of gas that's inside. And so we are looking at another quotient relationship, P1 over T1 equals P2 over T2. This can be rationalized as well. The faster the particles are moving at higher temperature, the more kinetic energy, the more they collide with the walls. Unlike what we saw earlier with the balloon where they could swell to offset that pressure, in this case the volume is maintained and those higher collisions just increase the pressure. This is what happens inside a bomb. So if we ignite a bomb and the temperature and the kinetic energy of the exploded molecules rapidly increases so that the pressure inside the case grows exponentially and gets to a point where the case can no longer contain the gas molecules, and so we get the explosion that comes with a bomb. So here's a sample problem for this. At what temperature will the pressure of a gas initially at 20 degrees Celsius and 700 torr reach 1/3 of the initial pressure? And so we're looking for temperature again. So we're looking for T2. We want to know at what temperature can I get my pressure now to be 1/3 of what it was originally. And this time we're measuring in torr, 700 torr. Torr, in case you need reminding, are just another measure of pressure. We have atmospheres, kilopascals, and torrs that we run across frequently, and torr essentially is just another name for a millimeter of mercury. And so 760 torr or 760 millimeters of mercury are each equivalent to 1 atmosphere, which is also equivalent to 101.3 kilopascals or 10,000 bars. Sorry, 10 to the 5th bars, not 10,000 bar. So there are lots of different pressure units that we use commonly, but torr is just another one of those. And so we're solving for T2. That says T1 over P1 times P2 is going to give me T2, just a little basic algebra. And so I know I'm starting at 20 degrees Celsius, but remember we never use Celsius in gas laws because Kelvin is the absolute temperature. And so we're going to convert that and make it 293 Kelvin. And this is for a pressure of 700 torr. I also know that I want to go down to 1/3 of 700 torr. So in writing it this way, instead of actually dividing 700 by 3 and putting the number down and writing it this way, it's quick for us to see. 700 torr cancels out, and so my temperature is going to decrease by 1/3. Again, it's a constant direct relationship. So if I'm going to bring the pressure down by 1/3, that means the temperature also had to fall by 1/3, and I see that my temperature falls to about 97.7 Kelvin. If I look at the contributions that I saw from those previous cases, I can begin to piece out what happens in each situation when we change the different things that affect gases. And we do that first because historically that's how these things were found. They were found one at a time. And so we know that volume's proportional to 1 over pressure. That's from Boyle. We know that volume is directly related to temperature from Charles, and Avogadro told us that volume is directly related to the number of particles present. And so we can work all this together into one overriding system. We can say that volume is proportional to the moles and the temperature, and is proportional to 1 over the pressure, so we can say it as NT over P. And then we define this variable R as a proportionality constant that would say those things are proportional by R. So it means that volume equals R times those things, or R times NT over P. If we want to put this in a more familiar form that maybe you've seen before, and put it into this huge, big, overriding equation called the ideal gas law, we get PV equals nRT. You'll hear me throughout the year refer to this as the Pivnert equation. Essentially, this combines all the different factors that affect gases, and all the other gas laws can be derived from this one simply by holding whatever variables need to be constant. For Boyle's law, for example, if we hold temperature and number of moles constant, we see PV equals R. And so that's our constant, where we said PV equals constant. R is that constant, also with the N and T involved as well. And so the ideal gas law can be used to solve questions where we're not at standard conditions and where we want to know about moles and where we have multiple things changing. So for example, we're not at standard temperature, we're not at standard pressure, we don't know if it's constant. Ideal gas law comes in and helps us out. So for example, the equation below says that I'm going to decompose calcium carbonate, and as I do this, I'm going to produce some CO2 gas, and I'm going to trap it in a 250 milliliter flask, and we know gases expand to fill their containers, so even if it's a little bit of gas, it's going to fill the 250 milliliter flask. And then after that decomposition is complete, we measure the pressure with a probe to be 1.3 atmospheres, and we have a thermometer in there that tells us the temperature is 31 degrees Celsius. And we want to know how many moles of CO2 gas this represents. So since we're looking for moles and we're not at standard temperatures and pressure, we're going to use Pivnert. PV equals nRT. We're looking for moles, so we'll do some algebra, rearrange so that we can see N equals PV over RT. My pressure was 1.3 atmospheres. My volume, like we said, was 0.25 liters. I have to use my temperature in Kelvin, so we convert 31 to 304 Kelvin. And then the R value of choice here is 0.0821 liter atmosphere per mole Kelvin. I've selected this R because we're working in atmospheres. Had we been working in kilopascals, it would have been perfectly acceptable to use 101.3 kilopascals for my pressures or whatever, and then use 8.31 liter kPa per mole Kelvin. That would have been perfectly acceptable. There are several values of R in your charts on your AP exam, so even if you come across something in TOR, you can just look up the R value that's appropriate for that. Once we solve for N, we see that it's 0.013 moles of CO2. So we're at a little bit higher pressure, but a very low volume, and a slightly higher than standard condition temperature. And so we're occupying a rather small amount of moles. There are some special uses of the ideal gas law. For example, gas density and molar mass. These can be arrived at mathematically. So if we let capital M equal molar mass, take PV equals nRT, do a little math on it, rearrange, see that N over V equals P over RT. We know that moles times molar mass equals grams or mass, and we can know that density equals mass over volume. So if we do some substitutions, we can see that density equals moles times mass over V, which happens to be equal to PM over RT. And so density equals Pm over RT.